So it corresponds to the paper submitted to the special volume. It's about constant time. Which time complexity classes make sense? Of course, polynomial time, but also linear time. It's not so common because it has machine independence characterization, for example, but also because there are many problems inside it. Constant time, it makes sense. For example, in database, you can have constant time procedure for update answers. You have given the answer, and you want to update it with an assertion of tuple. Also, in enumeration with constant delay, it has been used. For example, this example, you see it. The query, the first order query. It's very natural. It could be graph. The tuples can be enumerated, can be computed with constant delay after a processing, which is linear, and it's minimal. All constants, all algorithms using constant times need preprocessing, at least in linear. Of course, the model of computation is random access machine. Our model, what is it? I insist about native operations. It's exactly as you know, you have a program acting on infinite sequence of registers on the memory, but you have a reference register. It's very important. It is never modified during computation, and it gives also the size of the registers, the contents of registers. The program is, as you imagine, I insist about 5 instructions, operations, inside a set of operations which have been presented before. I'll give several examples. You get a reference number, or you read at any and output a register at any time. So I insist input and output instruction are executed at any time. So we have 5 constraints I've mentioned. Input must be less than Cn, linear, and the result also should be less than Cn. If not, it's forbidden. Overflow. This does not prevent to use larger integers, and it's equivalent to have register contains polynomial, provided that the addresses are linear. It can be proved. So it's robust in some sense. We need, for examples and so on, for the algorithms, to do programming and to adapt our RAM with several arrays, which are useful, for example, for preprocessing and variables too. And you use op expression for a set of operations, a finite set, of course. Example, you see at the end, a plus multiply expressions using indexes in arrays and addition, multiplication, and variables if necessary, and n, the integer, the reference integer. So the program is, as you can guess. It's not it's not surprising. You see it, and you say that this is a RAM with operation. You define your RAM with these operations, with set operations. I borrow a simulation defined by Yuri, lockstep. I'll use it in two examples. With a lag factor, which is a slowing down factor. What does it mean? It's difficult to read, I suppose, I assume. So the main thing is that the behavior of the second program compared to the first program is that it acts exactly as the first one with respect to input outputs. With respect to input outputs, when we are fixed, sorry, when we are fixed, when we have fixed the inputs, sequence of inputs, you fixed for the first program a computation and then a list of input output. Okay, sorry. It's the same. It's just that. It's a problem of contact. Yeah, exactly. But how to versions of RAMs simulate each other lockstep. It's not surprising. It's just an example. I insist on the fact that addition is used. Successor is not sufficient. You need it to encode arrays into memory. So an array element like AGX is represented, as we do in programming, by R, SX plus G. There's no multiplication because SX is XX repeated S times, and G is also a constant integer. So only addition. At the origin of this work, the choice, what must be the choice of native operations, how it influence complexity classes. Are the complexity classes of RAM with addition, multiplication, and subtraction equals to that if you have only addition, or if you include division or other operations, square root and so on. The central concept of work is that it's what we call constant time operation. Sorry. Constant time. An operation is constant time computable with preprocessing. With this notation, I use it everywhere in the slides. If for each fixed d, that means a degree, polynomial degree, there is a RAM using the set of operations m, such that for each reference integer n, and precomputes sometimes in time linear, and after reading some integer, any integers less than nd, polynomial in n, it computes the result in constant time. It needs that the result is polynomial, bipolynomial. So it can be broader it can be generalized, for example, for exponential. It's exactly the same definition. You have not to read, but you have to read, you have to compute in constant time the operation if the result is polynomial in the bound you have fixed, or it's not, you have an overflow. Oh, sorry. I need you. Really, I need your help at this time. So this definition makes sense for exponential. Sorry. Up. Yeah. The question at the origin of this work was a question asked by some researchers. Is division computable in constant time using only addition, subtraction, multiplication? In general, we don't include division. In formally, it is you revise the symbol, constant time with preprocessing, using addition, subtraction, and multiplication. It's okay for time. According to about half. Yes, division is constant. It's a very old result, in fact. Very old result. It's due to not to Knut, but to Poppenstein in 1960. You know, it's very classical. The main challenge is to find the most significant digit of a quotient. It's an exercise for students, not for students or pupils. We have to try several digits. How many? Which ones? And Poppenstein answered this question. Oh, I recall the classical point. The digits of a quotient is obtained by taking the most significant digit of dividend, first digit of divisor, equal y1. And Poppenstein proved that if y is sufficiently large, which can be obtained by multiplying if not, you multiply the divisor and the dividend by the same value, which is b divided by y plus 1. Oh, you cannot see, you cannot understand. So you define something which is approximated value of a quotient. The leading digits of a quotient, it's not the quotient, but leading digits, satisfy this approximation. Note writes, no matter how large B, doesn't depend on B, on the basis. I have not mentioned the basis. The trial quotient will never be more than 2 in a row. So, what is our constant? I agree. For division, it's what you guess. You first you standardize, you normalize your divisor if it is too small, not to multiply it so, and you use the approximation, and you determine the exact leading digit with 2 tests, using multiplication, essentially. The point is that the quotients we use, you have at least two spots where there is quotient, are read in tables pre-computed in real time using also addition, multiplication, and subtraction. It's like that. The real algorithm is the following. You convert your operands, x and y, to base A, special base. Not the square root, the cubic root for technical reasons. And you use pre-computed arrays for that. And you know that you have only 3D digits, a constant number of digits in this base. It has been done for that. And you compute the 3D digits by iterating 3D times the previous algorithm of Popper-Stein, or Knut, if you prefer. Recapitulation. The Euclidean division is computable in constant time with linear time preprocessing using addition, subtraction, multiplication, formulae, you see. You can prove more easily that using only addition this time, you can compute in constant time with linear preprocessing. Addition, it's almost obvious, but it's on polynomial integers. Subtraction and multiplication. Transitively, intuitively, you have div belongs to, can be computed using only addition. Why? And now I insist on closure properties of this class. Once more, I use lockstep simulation. If you have a set of operation, any set of operations, finite set, and another operation which is called small up, it's almost the same number, and you have a program using also this operation. You can, in some sense, eliminate this operation. Your program can be lockstep simulated by a program eliminating this operation after a linear time computation, preprocessing, using only the operation allowed. It's a very easy. You concatenate, sorry, the preprocessing, and each expression using operation is replaced with the call of a constant time operation procedure corresponding to the definition of the operation in the class with big O operation. A consequence of a fundamental lemma for sorry. I wrote it will be very difficult for you, very boring. I hope it's not completely. I resume the things. If you have a set of operation including addition, it's important. An operation which can be computed using its constant time with preprocessing, using this set of big operations, then each operation is in the bigger class. You can eliminate in this program, which computed, the operation, and this implies a kind of transitive result. For example, an example of application, if you have seen that division is computed in constant time, I skip linear processing, processing. And if we can do the same for addition, multiplication, and subtraction using only addition. Transitively, division can be computed in constant time using only addition. And this means that the class is robust. The thing is that this class is robust because there are several equalities, but much more, much more. I continue. Not only this. The problem is the robustness. First, also, the first problem maybe is how extensive is this class? It contains also exponential, factorial, binomial coefficient, rounded logarithm, rounded C root for any C. In all cases, the constant time procedure is recursive. And for the CM root, we use a Newton approximation algorithm method.
You're 20 minutes in. You have 35 to be 35 of the talk.
Thank you.
You have 15.
So I have time enough. Thank you. Thank you, Guillermo. Thank you for it. It's better now. A robust is the complexity class, this complexity class. Alors, there's two parts, native operations and preprocessing time. It's linear time. Is it mandatory? Not at all. I try to convince you. Can you replace the preprocessing linear time with square root of n, or polynomial in n, or n zero, small 0, 1, like log n and so on, or polylog n, without changing the class. How to reduce preprocessing time to square root, maybe the most important result. We have to recall the definition of what is mean constant time. It has been presented. You say for all d, there is a RAM MD. I insist on that. Such that for all n, reference integer, M or MD compute something in time linear, and after that, the operation is computed in constant time. Observe a universal quantification for all d, for all n. The intuitive idea of a proof, I don't give more, is that we can replace the reference integer n with its root, say root, n1, for a fixed integer, n at the power 1, so c. So it can be an epsilon, if you want. So the preprocessing time becomes, because we have changed the reference ender, in the order of n1, that means the root of n, any root. I am going to give a result, and the second result with another notation you see here. You write constant time with preprocessing Tn with for any function Tn, constructible function, in fact, with operation which has been fixed. If you have, if RAM op, which computes these operations in constant time with preprocessing of the Tn, but it must be more than linear time. It can be anything. The first result we have presented is not exactly what we can hope. It's with n we limit to n and c, but we have to add some, I cannot avoid it because they cannot be pre-compute in linear time. It's a problem. So we have a reverse result, but including mod and division, in fact, division. But if we increase the preprocessing time, it's not reduce, we enlarge. To make sense of equation, you must first define time beyond linear time. And this is very natural. A RAM operates in time Tn for any function, more than n. If it executes Tn or the Tn instructions, we register contents and addresses all the Tn. So in the sense, Tn is the second reference integer in addition to the first reference integer n. What about increasing preprocessing time? You can reduce. Using only addition, you can reduce. It's easier, in fact, nc to n. This implies this robustness result, which is satisfying. How much can you reduce? No, I do the inverse. How much can you reduce? You have reduced to n epsilon the time, provided you have more addition and mode, no, division and mode. But what about preprocessing reduced to n small odd one? There is no one doing that. There is no one doing that. This is proved by cardinality argument. It's very easy. We have to have more than tables of this size. More than, it's not sufficient to have this size. Yeah. It's not a question of time. It's a question of pre-computed objects. It's a little more than we want, but we have. I finished. I'm almost finished. I think.
No, you're good.
Thank you. Thank you. Indulgent. We are interested by closure properties in general. It's closed under composition, provided the interpreted values are polynomial. For example, you have this result because the intermediate results are polynomial. And this is the difficult point is that. On the other hand, we don't know how to reduce, how to compute this one. It's a classical object using cryptography and so on, because you have an intermediate result which is exponential. I cannot manage with it. I've done overflow if in the definition, because we have to give it explicitly. If we have to, implicitly, you can do something like that, but I don't know. A closure property for fast-growing, anecdotic. If you have an exponential functions like factorial, Fibonacci function, you have this result. It's not very difficult. The definition is here. It's a kind of inverse, okay? The main argument, the number of x such that after x is very small. And we can manage with data structures and so on, some tricks to do things. Okay? It was the main motivation, in fact. The class of complicity are independent of the number of operations. If you have addition, you can add all the operations I mentioned. And it's also true for at least linear time. This classical for input-output problems. It's invariant with respect to the set of needed operations. It follows from the similar results I mentioned, using the fundamental lemma, because I use two things. You have that you have lockstep simulation, but you use also pre-computed linear time procedure or auto-TN for this. So it's invariant. Which operations do not belong to this class? But there are local operations, arithmetical operations, but also local operations, the operation computable in linear time on Turing machine on cellular automata by the same proof. For example, not division, but this can be computed in linear time on cellular automata, not on Turing machines. Relationships between operations, which are very local, can be computed in this class using only addition, because the computation models are local. But if you take something as small as S0, it doesn't work because big Boolean sequences are not local. I'm finished. Happy birthday to you, Yuri. Many thanks to the organizers, and thanks to you, especially Yuri, for sharing the concern to identify robust complexity classes. I hope you have an example with good computational model, and for discussions, personal encouragement and support, especially for me, for my students also, in the 80s and 90s and all time. Thank you very much for your attention.